Welcome to DP Tutorials by Donny Jerva. In this teaching module, we will emphasize on a topic which is the equipotential surface and its properties. So, what is this equipotential surface? Let us confabulate point by point so that we will be clear. Then this equipotential surface is nothing but a surface which have the same potential at all its points. Okay? Now, when we are dealing with charges, that means all these charges will have electric field. Like for instance, over here, if I have a positive charge, if I have a charge which is plus Q, we know that this charge will produce electric lines of force. This is our intuitive idea. Okay? We have learned about this concept that the electric field lines or electric lines of force will be produced by this point charge. This is the illustration or the representation of the direction of the electric field lines produced by a point charge. Similarly, if I draw a surface surrounding these electric field lines, we will get some kind of an electric field. If I draw a surface surrounding these field lines, we will get some kind of a surface which is known as our electric field. Then, apart from that, we have also learned that if we want to bring a certain charge from infinity, say if I consider this charge plus Q naught, if I want to bring this charge up to this point where electric field is experienced, I have to do what? I have to do some work. That means there is some kind of a potential which is stored on that test charge plus Q naught in moving from one point to the other point. That is our potential. So this at every point within the surface, that means if the potential is the same, so that type of surface is known as what? Equipotential surface. This equipotential surface finds applications in the surfaces of all conductors. All conductors should have, the surface of all conductors should be an equipotential surface. The surfaces of all conductors should be an equipotential surface. Why? Because when charges move through the surface of a conductor, that means the voltage should always be constant. We know that the voltage in household power line transmission is 220 volts, whereas the current will change. And we will define later on that current is nothing but the flow of charges or charge per unit time. Then the amount of charges which flows inside the surface of all these wires will be in such a way that the potential throughout the surface of the wire will always be constant. So this is the most important concept of equipotential surface. Even the surface of the earth where we used to do earthing for electrical appliances, earth is also considered to be the equipotential surface, having potential at all points along the surface of the earth to be the same. Now, further, the surface in which every point has the same electric potential, that is defined as equipotential surface. And keep in mind that the equipotential surface is that type of surface in which the potential is constant throughout. Then this equipotential surface offers an attractive alternative visual picture in addition to the picture of the electric field lines. Now over here, if I consider this as charge plus Q, we know that when we move very close to the charge, the strength of the electric field increases. The strength of the electric field increases. We know that by definition, electric field due to a point charge is given by the expression 1 by 4 pi Okay, 1 by 4 pi epsilon naught q divided by r. So it depends upon the distance. When the distance is large, electric field will be small, and when the distance is less, electric field will be large. So that is why all these spherical surfaces which are drawn surrounding this charge, these themselves represents the equipotential surfaces uh, which are circular in nature and which are centered around this charge plus q. Now all these spherical surface 1 and 2 are very close to each other. When you look at this spherical surface or equipotential surface number 4, it is quite farther, which means that they are not equally spaced. Okay? They are not equally spaced. So from this representation, it is very clear that all these equipotential surfaces are not equally spaced, and all these charges are centered. Okay, all these charges are centered at the charge plus q. Yeah, or the charge plus q. So from this picture, it is very close that the more the when these equipotential surfaces are very close, when the equipotential surfaces are very close, when the equipotential surfaces are very close, it indicates, okay, it indicates that the strength of the electric field is also large. The strength of the electric field is also large. The strength of the electric field is also large. And at all points, if I consider for this spherical surface number 3, if I consider this point and at this point, if I take this point as P and if I take this point as Q, suppose the voltage over here might be 1 volts or 1 joule or 1 joule per coulomb. Okay, it might be the voltage over here also will be 1 joule per coulomb or simply 1 volts. Okay, or simply 1 volt. So all the points within the surface number 3 will have what? Will have the same potential. Will have the same potential. So from here, when all these spheres, the more the spheres are very close to each other, that means the more will be the electric field. The more will be the electric field. And from here also we will ponder upon some of the cases of this equipotential surface for a dipole. Now for a dipole and a system of charges like charges or unlike charges, the the representation of equipotential surface differs. Now if I consider for a system of dipole, that means over here this charge I will take as plus positive, and this charge will be what? This charge will be negative. Now we know that if we have a system of a dipole which is positive and the other which is negative, we know that there will be what? Electric lines of force. Okay, electric lines of force. Electric lines of force for a positive point charge will be directed radially outwards, and for a negative charge, okay, and for a negative charge, it will be directed radially what? Radially inwards. Radially inwards. This is the concept of electric field. Okay? This is the representation of electric field or electric lines of force. Then from here, when you look closely, that means for a dipole, all these lines of force will come from the positive charge and they will go into the negative charge, which means that these lines of force very near to the charges between plus q and minus q, these charges, okay, these electric lines of force will be very close to each other. That is why when you look at this picture of the equipotential surface of a dipole, all these equipotential surfaces are very close to one another. They are very close to one another, but keep in mind that these equipotential surfaces should not intersect one another. Even over here also, electric lines of force do not intersect with each other. And over here, the surface will be close. The surface will be close, but they should not intersect. Okay? If you look between this, suppose if I name this as spherical surface 1, spherical surface, equipotential surface 2, equipotential surface 3 and equipotential surface number 4. Then at these equipotential surfaces, that means when you look, that means farther from the charge, the electric lines of force are quite farther. And when you compare between these two unlike charges, which is a dipole, all these lines of force, electric lines of force, are very close. And over here also, all these equipotential surfaces are also very close to one another. Okay, so this is the representation of the equipotential surfaces of an electric dipole. Now, when you have a system of like charges will be positive charge and a positive charge, or it might be a negative charge and a negative charge. Now, for a system of like charges, if I draw the direction of the electric field lines, okay, over here all these charges will be in that way. Okay, even from here also these will be the direction of one of our electric field lines, but at the center, okay, at the center there will be no electric field lines. That means there's a neutral point over here. For all these will be the direction of one. All these will be the direction of our electric lines of force due to a system of like charges. So which means that these lines of force at somewhere in the region between these two charges will be very small, okay, or they will be largely spaced. Okay, largely spaced. So the representation of equipotential surface for a like charge or for a system of like charges, that means they will be largely spaced. Whereas from here, when you look for these charges, okay, away from their point, that means they will be very close to one another. So over here this will be closely spaced, over here this will be what? Largely spaced. This will be closely spaced. Over here largely spaced. Over here this will be closely spaced. Okay? Closely spaced. Largely spaced. So these are system for one. This will be for the representation of equipotential surface for like charge. So now we will move on into the discussion of the properties of equipotential surfaces. Now, the first point for the property of equipotential surface is that work done in moving a charge in an equipotential surface is zero. Now, let us consider that this is that charge plus Q, which is placed at the center. Then we know that there will be electric field produced by this cross charge, and it will be directed radially outwards. Now, if we take 2 points within this equipotential surface, if I draw a spherical surface, that means this will be an equipotential surface. All points on the equipotential surface should be equal to 0. That means over here, if VB is the voltage at B, point B, and VA is the voltage at point A, that means the magnitude of the voltage at B and at A should be the same. Now, if I take, suppose a charge Q0, let that charge Q0 be located at point B. If I want to move this charge, okay, or I intend to move this charge Q0 between these 2 points, what do I have to do? I have to apply a certain amount of work done. Okay, I have to do a certain amount of work done, which means in this case that if VA and VB are the electric potentials, then there will be one. If you are comparing between these 2 points A and these 2 points B, then there will be one. There will be a potential difference. So what is that potential difference in this case? Since we are moving from point B to point A, so point B will be considered okay, momentarily at a high potential, VA minus VB. So what is this VA minus VB? So electric potential difference. It is nothing but the amount of work done. That means you are moving this charge from point A up to point B. So this will be WAB, work done in moving the charge. I mean WBA. You are moving the charge from point B up to point A. Then from here, this will be work done in moving the charge from A to B, and this will be divided by Q naught. This will be divided by Q naught. WBA, okay, WBA, which implies that this work done will be equal to Q naught VB minus VA. So we'll mark this as equation number 1. And what is this WBA? WBA is nothing but the work done in moving the charge from A up to B. But for an equipotential surface, this is the most important point. The voltage at B is the same as the voltage at A. So when the voltage at B is equal to the voltage at A, so which means that equation number 1, okay, okay, WBA, I mean, okay, WBA, this WBA will be equal to Q naught. In place of VB, I will substitute by VA. So it will be VA minus VA. So VA minus VA will give you 1, will give you 0. So it will be Q naught into 0. So Q naught into 0 will give us 0, which physically means that this work done in moving this small charge between these 2 points A and B, moving the small test charge from point A up to point B will be 0, which means that if charges are moving within the equipotential surface, that work done in moving the charge over an equipotential surface will always be 0. In spite of that, charges still move. Okay? Charges still move. There will be work done, but the magnitude of the work done will be equal to 0. That means there will be no work done in the sense that still charges are moving. Okay, so which means that there will be some conservation. Okay, some conservation. That means work done. It is a conservative force. We define that as a conservative force. So which means that over here, if the work done is 0, things are what? Things are conserved. Okay? Things are conserved or conservative in nature. That means the work done in moving the charge between an equipotential surface is conservative. Okay? Is conservative in nature. Now, the second properties of equipotential surface is that the electric field is always perpendicular to the equipotential surface. Like for instance, over here, if I take this charge plus Q, we know that there will be electric field lines emanating from the charge plus Q, and let the equipotential surface be S. Okay, so likewise from here, at this point B, I can represent an electric lines of force. I will take this vector and then I will place over there, and this vector will be perpendicular to that point. Okay, this vector will be perpendicular to this point. So which means that this is our one. This is our electric field vector. Then if DL is, if I consider 2 points within the equipotential surface such that these 2 points are very close to each other, then DL will be that small line. Okay, so here we will consider the equipotential surface as and let F be the force, okay, to move a test charge Q0. That means over here at that point A, we will place a test charge Q0 and we will drive or we will move or we will exert a certain external force F on this charge at this particular point, moving from point A to point B within the equipotential surface. So from here, since we have this length dl, that means we can represent that length dl in terms of the displacement vector. So I will take this displacement vector and let that displacement vector act on that direction. But it is evident from here that this displacement vector represented by the yellow ray will be perpendicular. It will be at right angle. From the figure itself, it is very obvious that that angle is 90 degree. That angle is 90 degree. So we will try to prove that why this electric field is always perpendicular to the equipotential surface. Okay? Why is it perpendicular? So from here, we know that when you apply force, when you apply external force on this charge, the charge will be moving. When it moves, that means there will be work done associated, or the work done will be exhibited in that process, or the work done will be associated during that process. So what is work done? Work done is talking about force into displacement. So from here, this will be force, okay, force into displacement. What is that displacement? The displacement will be that dl bar. But what is force? Okay, what is force? Force over here, this will be what? Q0 into E. So from here we will write that equation and we will rewrite that as what? Q0 E dot dl. Q0 E dot dl. And we'll mark this as equation number 1. But before we write that as equation number 1, okay, we further write this in another format. Okay. This work done in moving the charge from E up to B, moving the charge from E up to B, this will be equal to Q0. Since over here it is the dot product of E and dl, we can write in terms of its angular form. Okay, angular form. So this will be E dl cos of the angle between them, which means over here that if this is E, okay, I can represent over here, if this is E, this is our vector E, and this is our vector dl bar, then this angle the angle between E and dl will be theta. So let us mark this as equation number 1. Okay. So from here, if VA and VB, that means over here similarly at point A and at point B, let VA and VB be the equipotential, be the electric potential or respective potential, then we can write the potential difference. Okay, then the potential difference, then the potential difference, then the potential difference. That means since we are moving from point A up to point B, we'll write VA minus VB. What is this constant? It is work done per unit charge. And from here, using equation 1, okay, using equation 1, or we can write below using equation 1, what is WAB? WAB will be Q0, okay, E dl cos of theta. This will be Q0. So from here, Q0 and Q0 will get cancelled. So we get, this will be E dl cos of theta. Okay, but what that surface is, okay, for that surface is, the potential at point A is equal to the potential at point B because it is 1. It is an equipotential surface. Because it is an equipotential surface. Now, if I mark this, if I mark that as equation number 2, which means that the left hand side of 2 will reduce to 0. The left hand side of 2 will reduce to 0. So which means over here this will be equal to 0. And this will be equal to E dl cos of theta. Which means that over here, when you look from the right hand side of this equation, which means that the right hand side of this equation, E dot dl cos of theta, the product will be equal to 1, 0. This will happen only if, if and only if this will take place if and only if theta is equal to 1, 90 degree. If theta is equal to 90 degree, cos of 90 degree is how much? Cos of 90 degree, it is equal to 0. So if you substitute on this equation, if you substitute on that equation, E dl cos of 90 degree, put on that equation, that means this result will give us to be equal to 1, will give us to be equal to 0. So which means that from here, it implies that E is perpendicular to dl. Electric field is perpendicular to dl. Therefore, the angle between them should be equal to 1, should be equal to 90 degree. Should be equal to 90 degree. So from here also, even if you take, irrespective of the points, if I take that point also, if I take this vector and represent it over here, that means if I take this vector, that means you can also find out over here that this angle, this angle between is how much? It is 90 degree, irrespective of all the points, irrespective of all the points. This is the direction of electric field. The electric field is perpendicular to 1. This direction, this electric field is perpendicular to the surface S. If I take from here also, this is the direction of the electric field, but this direction of the electric field is perpendicular to 1, is perpendicular to the surface S. So just go through those discussion, and then from here, this is the conclusion that the electric field is always perpendicular to the equipotential surface. Another important point, number 3, the spacing between the equipotential surface indicates the strength of the electric field. So from here, when we consider an equipotential surface, if I have a charge, if I have a charge which is plus q, these are what? These are our equipotential surface, and as we move away from the charge, all these equipotential surface will not be equally spaced. So when these are not equally spaced, the spacing between the equipotential surface indicates what? The strength of the electric field. So we know that there is a relation between the electric field with its corresponding electric potential. This electric field we have learned that is defined as the gradient, d dr or dv by dr. This is our what? This is our electric potential gradient. Electric potential gradient. So from here, if I take only this, suppose if I take this surface S, and if I take this point as X, and if I did this point as Y on this surface S, that means the potential at X and the potential at Y should be the same. Which means that over here, for a small change, that means that dV will always be 1, will always be constant. And this will be constant only for the case of 1, only for the case, it will be constant only for equipotential surface, or the surface having same amount of potential. So when you look from this equation, when you look from that equation, this is equal to E, and this will be, if it is equal to constant, that means we can write this as a constant divided by what? Divided by dr. So in physics, if you have equality and a constant sign, which means that that electric field is directly proportional to, or is inversely proportional to the distance, which means that over here, when you look closely onto that equation, that means when the spacing, this dr indicates the spacing, so when this dr is large, electric field will be small, and when this dr, the spacing between the equipotential surface is small, then this electric field will be what? That electric field will be large. So when you look closely from here, when the spacing is small, electric field is large. When the spacing is large, electric field is small. Spacing is large, electric field small. Spacing is very close, electric field will be large. So this is that physical interpretation. Okay? Physical interpretation of what? Of the spacing. The spacing between the equipotential surface indicates what? The strength of the electric field. You have to support the answer from the definition of what? Electric potential gradient. Okay? E equal minus dV by dr. That means from here our conclusion is that when the equipotential surfaces are very closely packed, that means the greater will be what? The strength of the electric field. I have explained over here. When dr is large, E will be small. And when dr is small, when this is very small, so the electric field will be what? Electric field will be large. Another important illustration is that the equipotential surface do not intersect with each other. They do not intersect with each other. It's like electric field lines also cannot intersect with each other. So from here, we have I have this charge plus Q, and we have put assumption that let there be two spherical surfaces which are intersecting at 2 points. Suppose they intersect at this point P, and the point of intersection is at point Q. With respect to the surface, suppose if I name this surface as surface number 1 and equipotential surface S2. With respect to S1, if you look with respect to S1, that means at that point P, the direction of the perpendicular will be in this way because that is the angle. Okay, number 1. So that is the way how to represent. So from here, and with respect to surface number 2, okay, what will be the with respect to surface number S2, what will be the perpendicular at point P? The perpendicular will be on this direction, 9 angle. But these two lines, okay, these two directions will be in at point P, which means with respect to S1 and S2, there will be two perpendiculars. There will be two perpendiculars, which is logically impossible. Okay, which is logically impossible. So, which means that that is why two equipotential surfaces should not intersect with each other. Okay, should not intersect with each other. So that is why, with respect to the surface, okay, with respect to the surface S1, this will be the direction represented by that blue curve, this orange ray. And with respect, the perpendicular with respect to this surface S2 at point P, it will be represented by this vector, okay, with that vector. So that is the angle. This is the angle which is perpendicular to 1, which is perpendicular with respect to the surface S1. Perpendicular with respect to the surface S1. Okay, and then S2, I mean. and then this will be 1. This will be the angle which is perpendicular with respect to 1, S1. Yes, this is 90 degree with respect to S1, and over here this is 90 degree with respect to 1, with respect to S2. Similarly, at point Q, with respect to S1, perpendicular will be on that direction. With respect to S2, perpendicular will be on this direction. So those are the illustration, which means that at one point there will be two perpendiculars. At one point there will be two perpendiculars. First, one will be this perpendicular, and another will be this perpendicular. So with respect to surface S1 at point Q, this will be the perpendicular. Okay, that will be the perpendicular. So this will be the perpendicular at point Q with respect to S1. And then another perpendicular at Q with respect to S2. So this will be the perpendicular with respect to S2 at that particular point. So from here, what will be the perpendicular? This, okay, double angle. This will be the perpendicular at point Q with respect to S2, which means that when the two equipotential surfaces intersect with each other, there will be two perpendiculars at that point of intersection, or at that point of crossing, which means that it is logically impossible. There should not be two directions of electric field lines at only one point. So this representation does not take place in nature. So these are some of the important properties related to the equipotential surface. You just go through the discussion right from the beginning so that you will understand the explanation and understand the concept. Thank you.